Right, so let's get started for the second part of the session. So yesterday we covered the TriCore basic knowledge that's basically needed to have a basic understanding about the architecture itself. And for today, we are going to cover point number 2 and 3, which related more to the tool chains that you are going to use on the TriCore architecture, the tasking tool chain. So the first point that will be covered today will be the compiler optimization. So we will see in this part the different optimization levels and how could you use the optimization pragmas for your use cases, and we will see as well a different independent core optimization algorithms like generic optimizations or the front end part of the compiler, and we will see as well core specific optimizations, which are the optimizations that related or core specific in this case, and sometimes it's called back-end optimizations. So this is the first part of the session. The second part we will have kind of example. How could you build multi-core based application on TriCore, and what are the points that you have to take care of in order to get the maximum performance on the TriCore using the tasking compiler. Just a quick note here. So we are going to have a new session on 21st of November. So it covers more the safety aspect of the tool chain. So we are going to discuss the different topics that's related to tool chain qualification according to ISO 26262. And by the way, it will not provide a specific knowledge for the TriCore tool chains that we are providing. It's a generic knowledge that you have to know in order to qualify whatever tool you are using in your development environment. And at the end, I will give you a bit as well about the hints of the next webinar, so you could decide yourself if this is interesting for you or not. All right, so let's get started. For the compiler optimizations, in order to get the best performance of your application on the TriCore, you have to optimize the tool chain. You have to use the tool chain in an optimized way. And the two main parts, big parts of the tool chain where they influence big performance impact on your application is definitely the compiler and the compiler part of the tool chain and the linker part of the tool chain. So these are basically the two main cornerstones when it comes to tool chain optimization. Yeah, definitely sometimes there are this assembler optimization, but it will not really provide a big impact in this case. So we will focus in this presentation on the compiler part and on the linker optimization part as well. You will find, optimization generally, it is a trade-off between code size and the performance. So some developers, you want to generate as the most optimized or the shortest size of the ELF file that you will generate out of your software stack. And some other developers, they have enough memory and they don't care too much about the code size. And what's important for them is to build the fastest applications that could run on the TriCore. And this is always the trade-off. So some people prefer performance optimization, some people prefer code optimizations. And in order to generally provide good optimization, it's based on some optimization flags. So this optimization flags together, they build something called optimization profile. So when I speak about the optimization profile, I mean the set of the optimization flags that I use in order to influence code size optimization or performance optimizations. And by the way, we will see here a couple of optimization profiles that are recommended from the tasking side. And in the next slides, I believe. So feel free to use these optimization profiles if you would like. And yeah, so generally the optimization process, it's kind of iterative iterative process. So it's not like a one steps that you need to take and that's it. No, it's kind of iterative process. So it's kind of looping here. So first you select a certain optimization profile with a certain optimization flags, and then you start executing your application, and then recording the results and comparing the results with the previous results before using this optimization flags, and see what could happen. And accordingly, you could change this optimization profiles based on your needs. So such iterative process could be easier for you if you use here something called its tasking embedded profiler. So it makes this iterative process for you. So it records the results before the optimization and after optimization, and it shows to you as well what could you do in terms of optimization if you would like. But this is a bit out of the scope at the moment, but if you would like to make this iterative optimization process, there is one optimization tool that you could use, and it will make definitely your life a bit easier. All right, so if you approach the optimization topic, you will find here there are two kinds of optimizations. The global optimization, which is I am applying here the full optimization profile on my whole source code or my whole software stack, and this will be our main focus for today. And you will find another kind of optimization, which is profiling driven based optimization. It's based on the global optimization, but as I mentioned, it will be a bit out of our scope today. All right, so for the compiler optimization, so we will see here the different optimization levels that the toolchain provided. We will see the optimization pragmas and how could you use it. We will see the front-end optimizations, back-end optimization algorithms, and then we will see more, because previously it's not enough flags. So we'll see more tasking compiler optimizations that could be out of interest for you. And this represents here the first part of this second session. All right, so let's get started with the optimization levels. So for the optimization levels here, you will find the tool chain offers 1, 2, 3, 4. It offers 4 optimization levels, level 0 to level 3. And after that, it offers as well a custom optimization where you could select even your own custom based optimization algorithms. So let's take it step by step. For level 1, which is for the level 0, which means no optimization. So that means I enforce as a tool chain not to optimize anything for me, and the mapping between the source code and the produced code, it will be kind of one-to-one mapping. So the compiler will not think too much how could you generate the best out of your source code. So the expressions, for example, it will be evaluated exactly in the same order that you already written in the source code. So there is no intelligence here provided by the compiler. There is a second level here, which is called level 1, which is called, okay, I would like to optimize, but I am a bit very conservative, and I don't like to optimize too much. So I would like only to optimize my application. So in this regard, this second optimization level, it's basically used if you face some debugging problems, debug your application on the hardware. So in this case, using the level 2 optimization, so if you decided for the level 2 optimization and you end up with some debugging problems, so it makes sense to get one level less in terms of optimization. So I will select level 1 optimization, and in this case, hopefully this debug related problem will goes away. As a third level here is optimize more. So I enforce the compiler. When I speak about compiler, I mean the tool chain. Yeah. So I will enforce the tool chain to generate the most optimization, which is a kind of just cherry pick points between speed and the size optimization. Yeah, and this is, by the way, the preferred option for the safety critical applications. So if you build a safety critical application, it's really very recommended to use this option here, which is a level 2, and the highest level optimization, which is a level 3, or the optimize more. This is here the highest level. So I'm really very aggressive when it comes to the optimization in order to meet my real-time requirements. So if you have really very critical real-time requirements and you cannot achieve such requirements using this level 2, yeah, okay, you could use this as this level 3, which is the highest level of the optimization. Or you could neglect all of these options here, optimization options, and you could define your own custom optimization if you would like as well. I would like to show it to you in a real life, not only presentation. So I will jump quickly to the tool chain. So this is here the tool chain that's provided by the tasking. It's Eclipse-based tool chain. I have here more than one project. So in order to select one of this optimization levels, so I just need to go here to the project and then go to the properties and then under C++ build and then go to the settings, and under this settings, if you go here to the C and C++ compiler and then optimizations, and here you could see the different levels that I already described for you. So 0 means no optimization, 3 means the highest level of optimization. And by the way, you don't really need to use the IDE in order to select whatever optimization levels that you are using. You could use all the options that are available as well from the command line. So you need only to check the user guide that we are delivering with every version, and you could see the mapping command line option where you could use instead of using this GUI interface. But yeah, definitely GUI makes your life a bit easier, definitely. All right, so let's jump to the next slide here, which is shows again to you the different optimization levels, and it shows to you this here. These are 16 letters that form together this optimization profile. So these are the optimization profiles recommended for every optimization level. So if you, for example, decided for level 1 optimization, so you could use this optimization profile, or you could use any of this optimization profile and make your own custom optimization profile. There should not be any problem with this. And here, every letter means something, and the meaning for every letter is described in this table. So you'll find here, for example, let's take, I don't know, let's take, for example, C. So if you go to know here what C means, so you go here to this flag. So C states here it's common sub-expression elimination. So this is a kind of optimization algorithm that's provided by the tool chain. And here there are this list of the optimization algorithms that you could use. And when the letter here, it's capital letter, so that means this option is deactivated. When it's small letter, it means this option is activated. So if you go here to check what are, for example, the differences between this optimization profile and this optimization profile, so I could say here, all right, so V here, for example, or W, V and W letters, they are here small, so it means it's here activated. And here in this optimization profile, it's deactivated. And what does V and W means? You could see here V and W means software pipelining and blah, blah, blah. So this is here the definitions of these letters. All right, so again, how to set an optimization level. As I show you, you could select it from the tasking GUI interface, or you could use as well the command line interface if you would like. So let's assume here I'm trying to compile a file that's called test.c. So you could call the compiler. So this is a TriCore compiler executable. So I am calling the the executable for the compiler, and then passing as a parameter the files that I need to compile. Or so by default, this will be optimized for the default optimization level, which is level 2. Like as I mentioned here, this is the default optimization. That's why I didn't specify anything here, and the compiler consider it as a default. Or I could define it explicitly and highlight it here with dash dash optimize equal to, so this is the second level, or simply by dash O2 as well, this is okay, or just say optimize, and the compiler will know, okay, you didn't specify any parameter, so I will take the 2 as a default value. Or you could specify only O, and it's the same as this, again, the compiler will know that you are talking about the default value here. So these are the two possibilities to set a certain optimization level, either from the command line or from the GUI interface as well. All right, so here you could use different optimization pragmas as well to enforce a certain optimization algorithms using this hash pragma. So hash pragma optimize and then put whatever optimization algorithms that you are interested in. And once you want to end this optimization algorithm for this C code segment, you will end up with this end optimize. So the source code or the code snippets that exists between this hash pragma definition will be consider applying this extra optimization for you. And if you think, why I need something like this, you need it because if you decided to define your optimization level globally on your whole project, that's okay. But sometimes you need to apply a certain specific optimizations on a certain specific code snippets. And in this case, this pragma, it will override what you already defined for your whole project. So this has a higher priority than what you already defined for your whole software stack. All right, so let's see here the compiler optimizations. So as we agreed, we have front-end optimizations that's not related to any core specific optimization, and the back-end optimization, which is based on specific core. And these are here the list of the optimization algorithms existed or provided for the front end, and these are the list of the back end optimizations that are provided for the back end. So I will not go through all of this optimization because we will spend time till tomorrow speaking about this optimization algorithms, but I will take kind of examples from front-end optimization and back-end optimization algorithms. So from the front-end optimization, I will take example here, the mill linking and mill splitting, because sometimes the customer use it, and lots of questions raised around this front-end optimization algorithms related to mill linking and mill splitting. So we'll see what it means for you and how could you use it for your sake. And generally, I put an appendix where you could, in the end of the presentation, where you could see how every single optimization algorithm work. So if you are interested to know exactly how the compiler optimize using one or more optimization algorithm, the definition or the how the algorithm works, it's already presented in the presentation. But as I mentioned, I will not go through it. Feel free to go through it yourself. All right, so let's cover here the mill linking and mill splitting. So for the mill linking, basically the concept is you have a front end and the back end, right? So the front end apply its optimization on the mill code, and this here you are having a different C files, and you will end up having a different mill code, and this mill codes will be the front end will apply its optimization definitely on the mill code, and then it will be passed as a single invocation to the C compiler, and the C compiler link all this mill code together and then apply the front end optimization one more time on the application level at this time, and then it will be passed to the back end. So once it's passed to the back end, it will generate a file. This is called asterisk.source file or single.source file, where the whole application will be generated. And please don't forget or take care, because this linking with the runtime libraries and the floating point libraries and the C libraries, it's still required in this case. Yeah, so linking against these libraries is still required with this mill linking. So you have here the front end optimization, and everything is linked and applied again, front end optimization one more time on the application level, and then passed to the back end. So this is here how the mill linking work. For the mill splitting, it works a bit different than the mid linking. So definitely you have the front end optimization of the compiler that already optimized on the mill code, and then the code passed to the C compiler mill link. It will link again the mill code on the application level. And then instead of calling the backend, as we already saw here in the mill linking, there will be mill splitting in this case. So the front end will generate here some intermediary form of files that's called MS files. So MS files, it stands for mill splitting files for every single file that's already provided. And after that, a backend will be applied on every single file. So as you could see here, it has advantages and disadvantages with this approach, because here the backend, it will not be aware about whole application level. It will be the optimization for the backend, it will be applied only on a certain modules, and doesn't take into consideration the whole application, as we already saw here in this mill linking part. So this is here the disadvantage of the mill splitting feature, but on the other hand, it provides as well some more effective build process, because the files that are generated here, this MS files, it will be updated for the parts of the applications that already changed, and not your whole application. So if you use, it's possible to use make utility in order to define for you a better build process. And definitely with this feature of the mill splitting, the build process will be way faster. All right, so let's see one more example here from the backend optimization, which is a code compaction. So the code compaction, the definition for the code compaction, it is the reverse of the code inlining. So inlining means I have a certain snippet of code, and I'm inserting it in a multiple parts of my code. And code compaction here means, okay, I found instances of the code that are replicated in more than one place on my application. So I will take all these instances of my code, and I will put it in a function, and then I will let every time I need this code, I will call the function and I will return back. So it has definitely an impact on the code size. So the code size, it will be less, but on the cost of the execution speed, because every time I need this code, I need to go and jump to the function and execute it and then return back. So this is here the code compaction feature. You will find here a very important compiler option that's called trade-off option. And so this option, it has impact on really a lot of compiler generated code. So we will see in the next slides how this option, this trade-off option will work. So for the trade-off option, it has a value of 0 till 4. So and inside this option, you are define if you are interested more in the speed optimization or you are interested more on the code optimization. So here is the trade-off value, it's 0, so it means I'm optimizing for the speed. If the trade-off value is a maximum, which is 4, means I'm optimizing more in the direction of the size. So in this case, it will generate less size of the ELF codes that we will flash on the ECU. And if you define this value as a 2, so it means okay, I don't have any bias in terms of optimization for speed or size, so I am kind of I'm okay for the speed and size optimization. And these are here the values of the trade-off. So for example, if you select as a trade-off value of 0 till 2, so a value of 0 or 1 or 2, so that means as a compiler will select here the smallest number of the cycles, because I'm caring too much about the speed and not the size. So the compiler will select the instructions that has the smallest number of the cycles. And if I select the trade-off value of the 3 or 4, which is here more on the direction of the size, so the compiler will select the instructions that has the smallest number of the bytes in order to generate the most less ELF file possible. All right, so here we have as well this trade-off value. It has an impact as well on the generated code of the switch statement. So if you have switch statements, implementation for this switch statement, sorry, the implementation for this switch statement, it will be either jump chain or jump table. So jump chain, it's basically a chain of jumps, and this provide an implementation for the different cases that are declared inside the switch statement. And for the jump table, it will be a table where the different parts or the different references to the different use cases, so the different cases will be existed. All right, so if you have here the value of the trade-off 0, it means I am optimizing more in the speed. So the compiler will take care to generate more 100% in terms of time, and the size, the compiler will not care at all about it. For 1, it will be 75% in terms of time, 25% in terms of size. And here for the size optimization, okay, so the compiler will not care anymore about this time. So 0% for the time and 100% consideration for the size. So this is how the compiler decide on which implementation for the switch statement, if it's jump chain or jump table. All right, so for the loop optimization, the trade-off as well has an impact on the loop optimization. So if it's 0 or 1 or 2, okay, so it's speed optimization, or the value of the trade-off 3 or 4, it will be for the size optimization. We will see more regarding this in the coming slides. You will find as well this trade-off value has a big impact on the function inlining. And as I mentioned, function inlining. So if you want to inline a certain function in your code or not, so it depends really on the trade of value. So here, this trade of value 0, 1, 2, 3, 4, and you have 2 factors in order to controlling this inlining process. So the first one, it's called inline maximum increment and inline maximum size. So let's have an example in order to illustrate how this works. So let's take example here 1. So the trade-off is 1. So that means the value for the increment maximum increment inline maximum increment will be 50, and the inline maximum size will be 25. What does this values means? It means the compiler will inline the functions that are basically smaller than or equal to 25 internal compiler units. So it's kind of unit defined internally for the compiler. So as long as the function doesn't exceed this 25 internal unit compiler, this will be inlined. And as long as the function itself or the code, it will not be expanded more than 50%, the compiler will select more functions to be inlined. So this is here how this looks like. All right, so as we agree, for the trade of 0, the code compaction is disabled because here I'm optimizing for the speed. So I don't need any of the code compaction in this case. 1 is still the same. I'm optimizing for the speed. That's why the code compaction is disabled. 2, okay, it's only code compaction for the matches outside the loops. So inside the loops, I will not make any code compactions. For 3 and 4, it is optimization for the size. So the code compaction of the matches outside in the loops, outside the loops, and matches inside the loops, as long as the frequency of this, it will be less than 10. And for the 4, the trade value of 4, so I will make a code compaction of matches outside the loops, inside the loops, with this frequency. Estimated frequency of execution frequency is less than or equal 100. So this is here how the code compaction is impacted based on this trade-off values compiler option. All right, so let's have a more tasking optimization options. So here we will cover more options that are really of interest when it comes to multi-core, and when it comes to alignment, and when it comes to as well to check how fast the compilation will happen. So for example, align here, if you remember the alignment that we discussed yesterday. So if you use this compiler option align, you could have a full control over the variables and the functions to be aligned. So in this case, all the variables and all the functions that are defined in this file that's called test.c will be aligned on 4-byte alignments. And here, this option that's called dash dash cache, and you give a directory here. So this will have a kind of impact on the speed of the compilation. So if you have maybe the compiler take too much time to compile your source code, so please consider this compiler option as well in order to accelerate a bit the compilation of your source code, because it will use a previous compilation output as long as you are using the same compiler version and you are using the same compiler options. And this is here how you invoke it from the command line. So you simply specify this directory for this dash dash cache, and that's it. All right, so you could check as well this compiler option that's called dash dash check. So this checks the compiler check for you if there are syntax error or not in your source code, and it will not generate any code in this case. So please take care, there is no code generation if you use this compiler option. So the compiler, it will check if you have a kind of syntax error or not, and definitely it's really more it's good for you because you don't really to wait. If you, let's say the compilation process take 20 minutes and you will get a kind of syntax error in the minute number 19. So it's not kind of the best experience that you need to experience, right? That's why it's, if you are in an early stage of the development, so it really make sense to make this option on, so the compiler will check all these syntax errors for you without generation of the code. All right, so more options here. So this code core association. So as the name it tells, it associates a certain code to a certain core. And here, this is the compiler command line syntax for this. And the value that you are going to assign, it will be one of the 3 values. So either clone or private and a number beside it, or share. So clone means multiple instances of this code will be associated for every core. So every core will get its own instance of this code. For the second option here, which is private and then a number beside it, it will be one code instance exist, and it will be executed by one core only. And for this third option here, that's called share. So there will be one code instance that will be executed or shared between all the cores that are existed on your hardware. So this is here, for example, I am using this assigning this private zero. So that means this code instance, it will be executed only on core number 0, right? So code number 1 and core number 2, it will not execute any of these codes because it doesn't have anyhow an access for this. All right, so this option here, it's called code section alignment. And again, from its name, it provides alignment for the section of the code here. So by default, the TriCore tasking compiler, it will align the code section to the minimum alignment requirements that are required by the TriCore, which is equal, by the way, it's 2 bytes, but you could definitely increase the alignment if you want 4 or to 8 bytes. It depends really on what you are going to do with the tool chain. So please consider this code section alignment if you want to increase the alignment for your code. And we have here a similar compiler options, but in this case for the data. So the data core association, so it will associate data to cores. So it's again 3 values. It's clone, and we already know what clone means. So a multiple instance of the data, 1 instance per core will be accessed. For private N, so that means only one data instance already existed and it's accessible only by one core. And for the share means the data will be shared between, it's only one instance of the data and it will be shared between all the cores. And this is here an example. So I assign here the data to this private one. So that means only core number 1 is able to have access to this data. And again, you could increase the data section alignments if you would like with this option, data section alignment. All right, so here we have more options that's related to as well as the memory location. So here you have this default near size. So if you remember, we already saw this option yesterday. So, if you define, for example, a certain data object and you didn't specify if it's a near or far, so the compiler itself, it will put it inside the near memory as long as the size of this object doesn't exceed the threshold that I already specified here. Yeah, and if it's already exceeded, so that means the data object is bigger than this threshold, so it will put not inside this near memory. For the second option here, we have default A0 size, and for the data that are accessible by this A0, yeah, so if you define this threshold here for this A0 size, and if the data it's bigger than the near threshold, but it's still inside the range of this threshold, so that means the compiler, it will assign it inside this A0 memory. And otherwise, if the data object it's bigger than this threshold, it will be assigned inside this far memory. It's similar as well to this compiler option here with this A1 size threshold. So here I'm assigning a certain threshold to A1 A1 based access memory, and as long as the data doesn't exceed this threshold, it will be saved inside this A1 memory. And if it's the data object it's bigger than this threshold, so it will be allocated inside the far memory. So here you have a full control really on which data will be assigned to which memory segment, if it's a near, or if it's A0, or if it's A1 as well. All right, so more compiler optimizations. So we have here this inline. So this inline, it will inline the functions that doesn't have this underscore underscore non-inline qualifier. So the compiler will inline functions as possible as he can. And this is an example for this inline. So you just specify this inline option in the command line. And again, we already saw these two options previously in the previous slides. So this is basically to control the inlining process, because it really doesn't make sense if you want to inline and you will end up with really very big codes that will not be able even to be flashed on your memory. So please take care to consider these two compiler options as well in order to control this inlining process. Okay, compact maximum size. So that means here, if you have the large sequence again of the code that occur more than one instant in your source code, this will be transformed into one function. And this option here, it will define the size of this. All right, I believe this is the last compiler related option. Slides. So here, this is the loop compiler option. So with this loop, you have a full control on which memory sections that will be aligned. So for example, here dash dash loop equal plus cache. So that means I'm enforcing the compiler to align the loops that are located inside the cache memory or the SPRAM. And if I define it with minus cache, not plus cache. So that means I enforce the compiler to align for an uncached memory inside this 0xA segment. And with this plus fusion means if there are more than one loop, so the compiler will fuse them together in only one loop as possible as he can. And here with this loop equal plus instructions. So in this case, a loop body with a number of instructions that are smaller than this threshold that you will define, this will be aligned. You could define as well with this plus size, and this plus size, it means the size of the loop in bytes. It will be aligned as long as it doesn't exceed this threshold that you will define. That's called dash dash loop dash size dash threshold. And the last option that we are having here is plus time. And plus time, it's related to the estimated cycle counts. So the loops will be aligned as long as the estimated cycle counts, it will not be exceeded this threshold. That's called dash dash loop dash cycle dash threshold. So this is here this compiler option that's called loop, and this is here the different combinations that you could use to force a different alignments for different loops. All right, so this is here the second part of the session. So enough with presentations. We will have a kind of example where we illustrate from early beginning till the end, how could you use the TriCore, and how could you use the tasking tool chain to build a multi-core based application. So believe it or not, this is the applications that we are going to build. So what we are going to do is we are having here a buffer that's called samples, okay? And this buffer, it has only values of zeros inside it, so it's initialized to zeros. And we have a semaphore, and this semaphore, it is synchronizing the access to this buffer, because we have here core number 1, core number 0, and core number 2. So we're having here 3 cores, and this core that's called core 1, it try to write to the buffer, and the core number 2 as well try to write to this buffer. And in order to organize this access to this buffer from 2 cores, we have this semaphore here. And for when, for example, core number 1 want to access, so first he has to look as a semaphore and then write to the buffer or read from the buffer, and then release the semaphore in order to let the core number 2 to access to lock the buffer, the semaphore, and then access the buffer again. So you will find here as well with this red text which core that exist. So this is here core number 0, this is core number 1, this is core number 2, and this is a code that's running on all cores. And this is here TriCore 1, so that means core 1, and this is here core 0 again, and this is here core 2. And as I mentioned, one core put a certain positive value to this a single element inside the buffer, and the other core put a reverse value of it. So that means if one core put, for example, +1, the other core put -1 to the same element inside the buffer. So that means the end value of this buffer will be 0, or at least the interpretation from what I already expected is the end value, the start value will be 0. The task here will be right. The task here will be right to the same location, and because it's a reverse action from every task, so that means the end value, it will be the same like the starting value or the initialized value. So we will see the results out of this example later on during the presentation. But yeah, let's get started how this basically built, or what is happening basically on the TriCore when we want to build this application from early start to the end of the application. So you could read this this figure here from left to right. So we start here. What is going to be started is the core number 0 always. So the core number 0, it will be started, and it will start executing the startup code. So C start, this is the startup code that is executed in the core number 0. And what is going to happen here is initializing the stack pointer. So what is happening with this startup code? Initializing the startup the stack pointer, and after that giving the green light for core number 1 and core number 2 to execute as well their startup codes. So at this point of time, here we have the startup code running on core number 0, we have the startup code running on core number 1, and we have the startup code running on core number 2. And because we have here different variables per core, so I cannot guarantee that I have here 3 variables. For example, I have here 4 variables, I have here 5 variables. So that means the amount of variables that are existed on every core, it's not the same. So, and accordingly, the execution of the startup code in every core, it will be execution time for the startup code in every code, it will be different. So, and the point here is, for example, if the startup code for core number 1 is faster than the startup code of core number 0, because here maybe there are less variables to be considered, it's not really very good idea to jump directly after the finish of the startup code of core number 1 and execute the application code or your logic. You have to really wait till the other startup codes to be finished, and then start executing your application code. Because let's assume, for example, the shared variables here, or the variables that are initialized by other cores. So let's assume I already finished the startup code here on the TriCore number 1, and I jump to execute the code that's related to the core number 1. But this application code needs some other variables that should be initialized by core number 1, by core number 0, or by core number 2. This is here a problem that could lead to a certain crash of your application. Yeah, and this is kind of as well a designing aspect that you have really take care when you decided for a certain compiler provider, how the startup code for you will run on the TriCore. So here we are using the tasking TriCore compiler, and in this case, uh, all the cores will wait for each other till the startup code of all the cores will be finished, and then we will start executing a different application codes based on the core ID that is existed for every core. But let's see here. So inside the startup code, maybe if you already use the tasking compiler, you could hit this tcx underscore end underscore init, which is the system variable that is used in order to wait for the other cores to be finished with the startup code. So I will show it to you in the reality. So if I take maybe this here as a copy and then jump back to the code here, and yeah, it doesn't really matter to select whatever project, because it is as a startup code, it's generated for you. So here, for example, you will find C-start, which is the startup code. This is a header file for this. And this is the implementation of the startup code that's running on core number 0. And there is definitely startup code that's run on core number 1 and as well for core number 2. So if I search here, you will find here for core number 0, you will find this variable, and this system variable, it's used in order to let the other let the cores to be synchronized in terms of startup code initialization. And once all the startup codes that's running on all the cores already finished, so I will know through this system variable. So this variable is defined here with this core number 0, and you will find the same variable here on the other cores. So let's select maybe core number 2. You will find as well here, this is a reference to this, and this is here definitely the extern, because it's already defined in the core number 0. And this is, as I mentioned, it is representing the initialization semaphore here. All right. Okay, so here in this figure, so you will find if you are building, for example, only a single core based application, you will end up with one main. But if you have a multi-core based application, how many main functions that you are having, you will end up again with only one main function, because the reason is simple. You have to have only one entry point, and you have to have only one function declaration for the main. Yeah. So once all these startup codes will finish, they will converge to a single point where all this startup code finished, and then based on a different core ID, a different execution path of your code will be executed. So I will use as well, or the AURIX, here in this case, provided some register where you could know which core that you are running your application on. And based on this information, a different code path will be executed. So if I am executing on core number 1, so a certain task will be fired. If I'm executing in core number 0, a certain other task will be fired. And if I'm executing in core number 2, certain other task will be fired. So you could consider here, this is, as I mentioned, you have only one main for a multi-core based application. And after that, this task that's called core 1 main or core 0 main or core 2 main, you could consider this as an entry point that's related only to a certain core. So you could consider you have here 2 levels or main, I would say. One main where the conversion of all the startup codes goes to, and then you will have a second kind of entry point for your, specifically for your core here. Okay, so as I mentioned here, we reach to the main, which is the conversion point of the all 3 cores. And once we reach to this point, so we are really ready to execute it, the functional part of my application. Yeah. So we have here 3 tasks. Task number 1, task number 2, and task number 3, or to be compliant with the course number. So task number 0, task number 1, and task number 2. So these are 3 different functions that are needed to execute it based on the function, based on the core ID that is available. And as I mentioned in the beginning, what task 1 does is incrementing the certain buffer elements, and what the task 2 does, it decrement the same buffer. So at the end, you will end up with the same value as the initialized value for the samples. What core 0 here does is it makes basically a synchronization and manage the whole application, yeah, the whole overall state application. So here it communicate as well with the core number 1, and it communicate as well with the core number 2, and at the end it will print the values of this buffer. So this is here the task that's defined for the core number 0. All right, so in the next part of the slides, we are going to discuss the implementation of this example. So we'll see basically the different project settings, we will see the language extensions, we are going to know what are the intrinsic functions are and how could you use it. And we are going to see the most challenging part, which is the linker scripts language and the linker script file. So all this we are going to discuss in the next slides. So we are still have a kind of a half an hour for this. Okay, so this is here. It tells you how you start your project using our tool chain and our IDE. So here it's 3 steps wizard. So it's a wizard based to start your project. So first you have to create a new project, and you have to definitely give it a name. And then you have to select here whatever families that you are interested in, if you are developing for AURIX first generation or second generation, and you have to select the device under, in this case, I selected this device TC37X. And because the IDE knows if it's a multi-core architecture or it has more than 1 core or not. So definitely in this case, it has more than 1 core. So it shows to you here, use configuration. I have to select all cores for a certain reason, yeah, because I'm developing a multi-core based application. So I have to select here, all cores will be used. And at the end, yeah, the last step here, you have to select the execution environment that you are going to use. So after you already develop the code, how could you test your code, or how could you see the results? So you could see here you have the option to select the simulator. So the simulator, it is on the IDE itself provided, and you could see your application flow using this instruction set simulator. And yeah, this is one option. Another option that's already available as well is you could select one of the application boards that are provided from Infineon. So it depends really if you, for example, have this hardware beside you, so you could definitely use it. If you don't have the hardware and you want to check your logic, so you could definitely use the instruction set simulator for this. And by the way, if you select a different devices, a different results will appear here under the targets for your device that you selected. Okay, so because we are building a multi-core based application, we have to do some extra ticks to some certain configurations. So you have to go to the right click on a project and then go to the properties, and under C++ build, you have to go to the startup configurations and then select the cores that are going to be used for your application. Yeah, so in this case, I have 6 cores. So as we agreed, core number 0, it's going to start automatically. That's why you cannot see here a start TC0. Yeah, so that's why you can't see here a start TC0. But yeah, because I am going to use the second core and I'm going to use a third core, so I will enable this start TC1 and start TC2. And by the way, by default, it's not enabled. So please, you have to take care to enable them if you need them. Okay. As we agreed, we have, despite it's a multi-core based application, we'll have only one main function. Because you have to declare only one declaration for a main. So this is here the entry point after all the cores will finish execution of their startup code. And inside the main, it's really very simple. So I will decide it using this who am I function. So this who am I function, it will return basically the core ID that I am using. So and then I will make switch case based on the core ID that case. So if it's core number 0, so okay, I will execute a function that's called core 0 underscore main, which is as I mentioned, it could be the entry point for the core number 0. And for case 1, so that means I'm executing the application on the core number 1. That's why I am going to execute the core 1 underscore main function, and then this is the same for the core number 2. If you have a look here on the who am I function, so it's inline function, and it uses this intrinsic function that's called underscore underscore MFCR, and you have to give it as an input core ID. So it will return as an integer as a core ID for you. So what is basically the question here is what is basically here this intrinsic function. So intrinsic functions, it's sometimes specific assembly functions, they don't have really equivalence in C. And the intrinsic functions, it gives you the possibility to use such functions. And such functions, they are developed by or already existed in the compiler. So they are provided by the compiler. And once the assembly code for your application is generated, the compiler will inject the related assembly mapped instructions for this intrinsic function inside your generated assembly. So this is basically the definition of the intrinsic function. And here you could see the tasking TriCore provides more than one intrinsic function based on your needs. So for example, this minimum function that returned as a minimum of 2 integers. For example, this knob, it insert no operation instructions into your code, to enable interrupts immediately after function entry. So if you are interested, please have a look on all these intrinsic functions, because it provides really very helpful input to you, and you are using it without any problem, as you see here, for example, with this underscore and underscore MFCR function. Okay, so here again, as we agreed, this core 0 main function, which is the task that's going to be executed on the core number 0, it keep track of the whole application, or the state of the whole application. Yeah. So I define here inside this code snippets, I define something called events. And this event here, I define it as a var, volatile, unassigned, and I assigned as well a certain alignment for this. It is on 4-byte alignments. Why all this information for this data object. I will define it shortly for you, but maybe for I could define for I could clear it for volatile. So volatile means this data object could be read and written at any time without yeah, for example, it makes sense for multi-threaded applications to highlight it with, for the data object to be volatile. So that means this could be written and read anytime. For far keyword, so this far keyword, I put it in front of the data object in order to have here a predictable section name. So for every for data, basically, the concept is for data, and for the code, the compiler will generate different sections. And with this far, I will have, for example, a certain predictable section name. So definitely you could define, for example, near if you would like, but in this case, I decided for to use this far keyword. And yeah, unassigned means unassigned, so that means it's always positive. Unsigned, and then underscore align, and then I assigned 4 value for the alignment. So that means the event, this data object, it will be aligned on 4 byte. Why I did this? Because maybe I could show it to you better on the in the code. So if I jump here again to the application code that I already prepared, I will set it here as an active project. And if you go here to the main, and if you go here to so this is the task that's going to be executed in the core number 0, and this is here the event definition. And the event, if you go here to set event, for example, you see the definition of this set event. It's going to use this function, and this function is intrinsic function. And because this is intrinsic function, and it put some requirement that the alignment for all these parameters, they have to be aligned on 4 byte alignment. That's why I set here the values that you could see inside the main task with for alignment in order to comply with the requirements that are needed with this intrinsic function here. That's why you could see here inside the presentation that yeah, it's defined as far, it's defined as volatile, it's defined as unsigned, and again, the alignment is 4 bytes. So I hope this is clear enough. Okay, so this is, we already covered. It's really very important as well to see how this task communicate with the other cores. So let's see here. Let's see here how this task communicate with the other cores. So what does this task means? As I mentioned, it uses who am I function, which is assert the value to be 0. So that means this task will be running on the core number 0. And here I make some initialize some pointers to this buffer that that is defined here. So this is a buffer that you already as well saw here inside the presentation. Where was it? So this is here the buffer, the samples buffer that you already saw in the presentation. And then the communication between this core, which is core number 0, and the other cores, it will be went through this event. So here I'm setting the event, okay, event core 0 preparation is done, and the other cores, they are waiting to till this event is fired, and then the execution will happen on the other 2 cores as well. So this is how the communication between core number 0 and the other cores happens. And then this core is still waiting till the other cores already finish the job. And then once it's finished, so this it will comes back, and then it will print the results, which is values of the sample buffer. So this is here the flow. Okay, so if I go back here to the presentation again, yeah, so we already saw how this task already communicate with the other tasks. Let's see what are going to happen on the other tasks. So this is a task that's happened on core number 1, and this is a task that's happened or executed on core number 2. And yeah, so as I mentioned, for every task, it uses who am I function in order to define on which core this code is running. So in this case, I'm asserting it to be core number 1, and here I'm asserting it to be core number 2. And then I'm this core, both cores, they are waiting for the starting core, which is core number 0, to fire this event. And once this event is fired, what's going here to happen is for every task it look or requests the semaphore, adding certain delta to the elements of the buffer, and then release the semaphore again. And it is the same as well for this task. So this is here what is going to happen. So if the value is 0 of 1 at the beginning for this sample buffer, and if I increment the value with this value and the other core decrement it with this value, so you will end up with the value of 0 again that's existed inside the buffer, right? Okay. So yeah, and again, I use some intrinsic functions here for this semaphore, to request the semaphore and to release the semaphore. And this is the intrinsic function for this. And yeah, once this is done, this task and this task, they are firing this event, which will be notified to the core number 0, and then the core number 0 will print the values for this. Okay, so let's have a bit overview about how the memory looks like, because as you already saw, we already declared here some data elements, so this event and this semaphore. And generally, the linker will allocate this data that we are speaking about, and the code as well, in cached memory, which is something good, by the way, but it's not really very good when it comes to the shared variables, because for every core it has its own cache, and in the TriCore there is no coherence between these caches. So that means for every different cache, once a value is updated, it will not update it automatically to the other values inside the other caches. And this is here a kind of problem. That's why it's really very important to make sure that this data objects, it will not be resided inside the cache. And how could you do that? You could do that in 2 steps. So first, you have to decide where you are going to locate such data objects. So I decided for this case to locate it inside the LMU. So the local memory unit, this is the place where I decided to locate my data in. And if you remember from the previous presentation yesterday, um, there are memory segments where the code will be cached, and there are memory segments where the code will not be cached. So for 0x9, the code will be cached and the data will be cached, and 0xp segment, the data and the code will not be cached. I will go quickly to it just to refresh your memory in this regard to the previous presentation yesterday. So okay, so this is here the data cache, and we are using the local memory unit. So if I want the data to be cached, I will locate the data in this 0x9 segment. And if I don't want the data to be cached, I will locate the data in the 0xb segment. Why not 0xa? Because I'm using the LMU. And definitely you have to take care to enable or to satisfy all the other conditions as well, which is okay. If you want the data to be cached, you have to um, uh, make sure that this decache bypass is deactivated, and the decache is by default to be enabled. Okay, so I will go back to where I was. Okay, so I will locate the data objects inside 0xb segment, which is it will not be cached. All right. And yeah, first as well, it's really good to find as well the section names that will be assigned for the events and semaphore and the symbol data objects. I will give you a bit about it from the IDE. It will be better to show it in the IDE. So I will jump here back to, oh, I have to exit the full mode. I will jump here to again to the IDE, and here let's go again to this example. So in order to see the results of the linker, you have to check this map file. So it's not generated by default. So if you want to generate it, please just right click on the project and then go to the properties, and then again C++ build settings, and you go to the linker, and under this linker, I believe this map file, yeah, and here you could find this generate map file. And once this is ticked and apply, you recompile, and then the map file will be generated for you. This is how to enable this option from the IDE. All right, so this is here the generated map file for my application. And as you could see here, these are the sections, the different sections, this here. The different sections that the compiler already generated for me. So this is here the section name. This always the first part here. It's always a section name. So this is RO data or dot data or dot BSS or dot text or whatsoever. So we are going to see what is basically the meaning of such stuff in a short. But yeah, you have to locate such information as well for the data objects that you already defined, which is the events and the sim buffer and the samples data object. So as you already saw here inside the IDE, so the section here, it contains of different parts. So this is here the formula where you could understand from how this section is formulated. So first you have to, or the linker shows to you this section type prefix. So this is a prefix for the section type. And then with this brackets, you will find this dot uncached. So it's really very rare to see it because it's related to the automatic variables. So if it's not automatic variables declared, this will be goes away. And for the core association, so for the core associations, as we saw in the first part of this second session, so you will have here 3 values if it's shared or private, and the number of the core besides the private or clone. So these are the 3 values that existed for this core association. And then the module name. This is a module where your data object or the function already exists. And then the symbol name. And the symbol name here, this is the name of the data object that you already defined or the function that you already defined. Okay, so so at least this is here the formula from where the linker will generate the different sections for you. So now you could interpret all this with yourself. But please take care, because for the interrupts, for the interrupt vectors and for the trap vectors, there will be a different formula. So you will find the first part of the generated section, it will be dot text. So that means dot text, it's a code, and then interrupt table, and then n, and then dot, and then interrupt vector, and then dot, and then vector number. And it's a similar thing for the traps as well. I would like to show it as well here inside the map file. So this is how it looks like. So the text. So these are the generated sections for the trap vector. So this is the text, and this is trap table 0, and then the trap vector, and this is a vector number. And yeah, this is here for the core number 0. This is here for the core number 1, and this is here for the core number 2. Yeah. So I already enabled only 3 cores. That's why you can't see the rest of the sections are generated, because I didn't even start them and I have nothing to do with them. So that's why you can't see them here. All right. So sometimes, for certain reasons, you need to rename the sections. So you could use this renaming pragma in order to change the section name. So, and after you already change the section name, you will end up with this formula. So this formula, it's the same like previously, but additionally, you will get this pragma value that you are going to define associated to your section name. All right, so what does RO data mean? What does the text means? What does the data mean? The BSS mean? All this has a certain meaning. And in order to interpret this, you have to check this table that I prepared for you. So this table, it contains basically the section type and the prefix that you see inside the generated part of the section name, and it covers everything here. So all you need to do is, okay, I have here, for example, this RO data. What is RO data means? So I will search here for RO data. So RO data. So here, so this is the RO data, and this RO data, it's for this section type var rom, and when you already defined for the constant var data. So this is here the description, and this is the name prefix, and this is the section type, and the rule is applied for all the sections. So all you need to do is you have to look at this section definition, and then jump back here to the table in order to get a better understanding what this section does. So for example, as well here, if you see this dot text, so the text here, this is for the section type code, and this is basically for the program code. Yeah, it makes sense. And so on for the rest of the section types. So we have still 6 minutes. I will try to be a bit faster. Okay, so as we agree here, you could rename the section if you would like, using the pragma. So you have here 2 pragma, so this pragma section, and then type, and then you put the name that you are interested in, and here pragma section, and then all, and then you put the name that you are interested in. So here, it's applied only for this type of the section, and this is here applied for the all sections, as the description explained itself. So let's have an example for this. So if I put, for example, this hash pragma section, and then this near data, and I put a name called where. So if I have a look on the tables that we saw in the previous slide, so this near data, the prefix for the section, it will be .z data, and after I apply this pragma, the generated section, it will be this .z data .where, and where, this is here the name that I give to this section. And yeah, sometimes you could use the other stuff as well. So you could use, for example, pragma section and then put the type. So this, it will put the section to its conformant to its prefix, this pragma section type, and then put the default. So this will restore as the default value. And if you put this pragma section restore, it will restore, but to the previous settings of this hash section, hash pragma section type. So this is here the different combinations of this pragma, and this is applied on this type. And here the difference between this and this is, here I'm specifying it to a certain type. Here I am generalizing it to all the sections that are existed. And by the way, please take care. You could use as well the command line option from the compiler that's called rename section, if you would like, or if you want to have a look on it. Okay. So maybe you already noticed that when you rename the section, the module name and the symbol name, they will go away out of the section, which is sometimes not preferable for some developers. So there are this pragmas that you could enforce the linker to put the module name and to put the symbol name inside the generated section. So feel free to use it if you want to put the module name and the symbol name as well. Let's have an example here. So let's assume here we are starting from here. So the text data, this is for the code, and the data, this is for the data. And I put, for example, hash pragma section all, and I give this name, rename one. So this, it will be applied to everything. So all the sections, right? That's why you see here, this is the updated section. It will be .text .rename one, and the data section as well, it will be updated with .data .rename one. So all the sections will be updated. And based on this results, if I write this pragma section code and then rename to, so this will change only the code type of the section. So it will be influencing only the text section, and it has nothing to do with this data section. And based on these results, if I use this hash pragma code without defining anything beside it, so that means here the I will put the default values, which is here this .text. Why this doesn't change? Because I define it only for the code part, right? That's why this data section, it still holds the old value of it. Okay, so let's see a bit of organizing work. Maybe it's really very useful to check in your case, which is using grouping inside this LSL file. So the LSL contains basically the configuration, and if you have extra customizations that you want to do on your data or on your objects, you could describe inside this LSL file or linker script file. And in this case, what I want to do is I want to make certain grouping for certain variables. Yeah, so as you remember, we already defined 3 variables or 3 data objects. It's event, it's semaphore, and this circular buffer. So these are the 3 elements that we already defined in our application. And the problem here is, if you go back to this linker map file, you could see here the data should be somewhere here, but it's really takes too much time till you put the proper data, because it doesn't belong to any of the groups, right? So it really makes sense to group the elements that has a certain logic, for example, that has a certain intent in one group. This will make your life a bit easier, because it really doesn't make sense to go through all this and search for some variables inside it. And this is here what I already made it for you. So I grouped as the definitions of these 3 data objects in one group, and this group, it's called not cached. And the results of this grouping you will see inside the map file. So here, if I go back to the map file and see again, you will find here, this is a group. So this here, all the three variables, they are belong to the same group. And it's kind of organizing things that could save you really a lot of time in a later stage. Okay. Let's see more about the map file. So we are a bit behind the schedule, but let's finish it. Yeah, so we already saw this task that has a name of core 0 underscore main that's related to core number 0, that's associated to BSPR or program scratchpad RAM 0, and for core 1 underscore main, it's associated to BSPR 1, and for 2, 2. You will have here this copy section that must be created at the beginning and in an automated way to allow the startup code to install such copy tables for you. And you could see sometimes the elements here inside the map file between these brackets. And this is here the definition of this copy section. So that means the section already has two entries here inside this map file. So you will find here it is located in the BSPR0 for the core 0 underscore main. And there is a ROM copy that's already existed in the program flash 0, and you could see here in the program flash 0, and from where I could get the conclusion that it is a copy section, because it is between these brackets here, as you could see. So if it's between brackets, so it's a copy section. And here you could see as well here how it is assigned to this BSPR0. Okay, so I use the TriCore tasking debugger in order to debug my application. So this is here kind of snapshot about how the debugger looks like. So here I could see the different cores and different threads that are running for every core, and this is here the results, and this is the output of the values of the circular buffer that I already defined. And yeah, this results, it is with using the semaphore, and this results is without using the semaphore. So before interpreting the results, I would like to go back here to show you the semaphore that I already used. So inside this main. So for example, this task that's running with core number 1, it uses semaphore. So it requests the semaphore, it writes a value, and then it releases the semaphore again. And it is the same as well for core number 2. It requests the semaphore, write a value or a negative value of the value written by core number 1, and then release the semaphore again. So this is here one instant. Another instant that I use in my application here is without the semaphore. So that means I already removed the semaphore from this task for core number 2, and again I remove it from this task that's related to core number 1, and then run the application again and see the results. And this is here the results. So the results with the semaphore, it's exactly what as I expected. The circular buffer at the beginning, it was zeros. Task number 1 written a positive value, task number 2 written a negative value, and then I printed the buffer again, so it stays the same with the 0, which is the initialized value, which is kind of logical thing. But without using the semaphore, this is the results that I already I already get. So this is, it's minus 10 times the value written by the task number 2. So why is this like why this happens, and why it's not like the previously expected results? It is basically a function on this generated assembly and the performance with and without the semaphore. So let's have a look here. This is a generated assembly that's already existed for for this TriCore core number 1, and this is generated assembly for core number 2. And yeah, so here you could see from the debugger, I could see the execution. So this is the assembly that's running on core number 1. This is the assembly that's running on core number 2. These are a bit of register values, and this is a pointer that's referred to. These are the pointers that refer to the circular buffer. So here, the core number 1 write a positive value to the element, one element of the singular buffer, and after that, directly the value is overwritten by the core number 2. So it will written with this minus 0.00625, and once you repeat this result 10 times, you will end up with this dash minus 0.6 value, which is what you already get here. So without the semaphore, the value, it will be directly overwritten with this TriCore core number 2, and that's why you already saw this bit of weird results here. All right, so maybe this is the last slide. So from the software configuration, I prepared a kind of a checklist that you need to check for your software. So first, you have to check your compiler configurations, and for your compiler configurations, you could see here inside this generated .src file. So if you go here back to the environment and under the debug, you could see this is here the source files that are generated, and here you could see these are the compiler options that are available or used in this case. All right, so it makes more sense as well to have a look on the map file, because it gives you a full overview about the different segments that are existed, and where the data and the code are located. And yeah, if you want to use this cacheable segments, please make sure that you are located the code and the data inside these cacheable segments. Otherwise, it will not be cached, and you are going to be wonder why my code it will not be cached. If you use the floating processing unit, so please make sure that you are, if you have already this coprocessor for this, so please use it and make sure it doesn't use this emulation memory. And how to make sure this is the case, that I'm using the floating processing unit and not as the emulation memory. So you will find inside the map file this libc_fpu, libcs_fpu, and libfp_fpu libraries. And again, please make sure to use double as single. So because single precision, this is way more optimized for the TriCore. So please make sure to make this option as well available, and please link against this libcs_fpu library instead of the normal library, which is libc_fpu. With this part, so I think I already finished. Sorry to be a bit long, sorry to be a bit fast to speak, but as you could see, the content is really very technical, and I couldn't be faster.
Okay, thank you very much, Ahmed.
No problem, Franz. Just one more slide. I forgot.
Yeah.
Sorry about this.
Okay.
So till now, we already cover the TriCore architecture. We already cover the compiler optimization. We saw an example about the TriCore. I will give you now a kind of idea what we are going to discuss in the next seminar. So for the next seminar, this is more interesting topic for the safety engineers, maybe, because we are going to shows you how could you qualify the, our tasking tool chain that you are going to use for your multi-core critical critical applications, and it is basically 2 stages. So here we are going to discuss the first stage, which is called tool classification, and after that we are going to see the second phase, which is called tool qualification. For the first part, which is related to the tool classification, we are going to give you idea how could you define the tool impact, how could you define the tool error detection, and these 2 elements together, this TI and the TD, they will give you the something called TCL, or tool confidence level. And this tool confidence level, it will tell you if you need to qualify the tool chain that, or any tool that you are going to use or not. So for example, if it's TCL number 1 or TCL 1 or tool confidence level 1, so in this case you don't need to qualify the tool anymore. If it's tool confidence level 2 or 3, so you will end up with yes, we need to qualify this tool, and associated with this ASIL level, you will end up with certain qualification method that you need to apply in order to get the work products that you need in order to pass the qualification. So this is the workflow that we are going to discuss in the next webinar. As I mentioned, it's really interesting topic to the safety engineers, and at the same time, what we are going to cover, it's not really a specific knowledge. It's really very general knowledge that you are going to apply to any tools that you are going to use during your development of your applications. By these slides, I am done.
Okay, thank you. By the way, these